Okay, let's dive into something we all just take for granted. We're going to go behind the curtain of our electrical grid. We're going to answer a question that is way more complex and, frankly, a lot more dangerous than you might think.
I mean, really think about it. You flip a switch, the lights come on. Easy. But what's the first switch? The one that gets the whole show on the road?
Well, you probably guessed it's not that simple, right? There's no giant red on button for a machine that can power hundreds of thousands of homes. So how do they actually do it?
The answer, the real answer, is right here. It's in a 156-page technical document. This isn't just any manual. This is the official set of instructions for a single steam turbine, a machine that can power a whole city by itself.
So that's what we're going to do. We're going to walk through this manual together, and we are going to start this thing up from a dead stop all the way to full power.
All right, first things first, let's just get a sense of the scale here. What exactly are we dealing with? Just how big is this beast? This table is pulled straight from the manual, and wow, it really tells a story. Don't worry about reading the whole thing, just look at the dimensions. We're talking about a machine that's almost 28 meters long and over 7 meters high. This is no garage project. This is an absolute industrial titan.
And then there's this number, 600 megawatts. So what does that even mean? Well, it's enough electricity for roughly 500,000 homes, all from this one single machine.
And to make all that power, its massive rotor has to spin at 3,000 revolutions per minute. That is 50 rotations every single second. Hang on to that number, because that's our destination.
But listen, before we can even think about hitting that speed, we have got to get through this absolutely daunting pre-start checklist. The manual is crystal clear. If any one of these conditions isn't met, you are prohibited from starting. No exceptions, period.
And this isn't about being picky, this is about preventing a catastrophic failure. I mean, look at some of these. If the rotor is off-center by just the width of a human hair, 0.075 millimeters, the whole thing's a no-go. If the steam is too cold compared to the metal, you could cause thermal shock and literally crack the rotor. And my favorite one is this. You cannot start the turbine if you don't know why it shut down last time. Makes sense, right?
So once everything finally checks out, the process of waking this giant can begin. And it starts incredibly, almost impossibly slow.
The very first step is to use something called the turning gear. It's basically a smaller motor that starts rotating that massive turbine shaft at just over 3 revolutions per minute. It's this super slow, deliberate crawl, just to make sure everything is perfectly aligned and to keep the huge rotor from sagging under its own weight. And I love this part because it shows you the human element. At this stage, the manual literally tells operators to just listen. In this world of high-tech sensors and digital readouts, one of the most critical checks comes down to the trained ear of an engineer listening for the faintest scrape or any sound that's just not right.
So, after that initial slow roll, the first real blast of steam comes in, pushing the turbine to its first big milestone, 600 RPM. And here, they hold the speed steady, checking again for any hint of friction or instability, as the machine starts to find its rhythm.
Now from here on out, the journey to 3,000 RPM is all about a series of carefully managed steps. It's a game of heat, pressure, and a whole lot of patience.
Just look at this process. The next big jump is up to 2,000 RPM. And then they just wait for 2.5 hours. This heat soak is absolutely critical. It lets the temperature spread evenly through tons and tons of metal, which prevents stress and fatigue that could cause a failure later on. Only after all that time can they finally push toward the final speed.
And let's talk about that heat for a second. The main steam that's blasting into this thing is 538 degrees Celsius. To put that in perspective, that is hotter than the inside of a professional wood-fired pizza oven. This entire 28-meter-long machine has to work perfectly at temperatures that would just incinerate almost anything else. So after hours of careful checks, that long gradual heating process, and incredibly precise control, the turbine finally hits its target. There it is, 3,000 revolutions per minute. The giant is officially awake, and it's now ready to be connected to the grid to start making some serious power.
But, getting up to speed is really only half the battle. A machine this powerful, this extreme, it needs an equally powerful safety net. So what happens if something goes wrong?
Well, that is the job of the Emergency Trip System, or ETS.
You can think of it as the turbine's nervous system and its self-preservation instinct all rolled into one. It is constantly monitoring dozens of things at once, and its only job is to shut everything down before a small problem becomes a huge disaster.
And this system is designed to be completely unforgiving. Any one of these conditions, and it triggers an instant, automatic shutdown. If the turbine overspeeds by just 10%, bam, it trips. If a critical lubricant line loses pressure, it trips. If that massive rotor shifts forward or backward by just a single millimeter, it trips. It is an absolutely vital layer of protection.
And there you have it, a 156-page journey, hours of careful, meticulous procedure, and this incredible symphony of immense heat and pressure, all of it culminating in the simple, reliable electricity that we use every single day. It really makes you appreciate the massive, invisible machinery that's humming away, powering our entire world.